we have this time we have a rectangular box. So x, y, and z are the dimensions of that box, and they're not necessarily the same anymore. So we have x, y, and z. And we want to know about the length of the box's diagonal. So if we go by diagonal, I think they mean the longest distance across that box. So we go from one corner to the far opposite corner. So we want to figure out a relationship between s, x, y, and z. So we need to figure out, how do you get that diagonal length s from those? Well, we can get it by applying the Pythagorean theorem. So if you look at the shadow of the diagonal, that's a line in the base of the box. And so from the Pythagorean theorem, let me label that line L. L squared is x squared plus y squared. Now, if you look at the diagonal, that's actually the hypotenuse of a right triangle, where the one leg is L and the other side is z. So s squared should be L squared plus z squared. But then we just figured out that L squared is x squared plus y squared plus z squared. So the diagonal length s is equal to the square root of x squared plus y squared plus z squared. Okay. So it says, assuming that x, y, and z are differentiable functions of t, okay, so they're changing in time, then how will the diagonal length change with time? What will be its relationship to dx dt, dy dt, and dz dt? Well, one option would be to work with this square root. You have x squared plus y squared plus z squared all to the 1/2 power, so ds dt. If we differentiate this side with respect to t, and we differentiate this side, the half will come down. We'll get x squared plus y squared plus z squared to the negative 1/2, and then we'll have to multiply that by the derivative of the inside. Let's see, the derivative of the inside, the root of x squared would be 2x dx dt, and the derivative of y squared would be 2y dy dt, and the derivative of z squared would be 2z dz dt. So we have this relationship here. I notice that there's a 2 in each of these, so it could be factored out to cancel with this 1/2, and so we would have finally ds dt equals, let's see, this is a square root downstairs. In fact, it's s, isn't it? So it would be, we have x dx dt plus y dy dt plus z dz dt all over this square root, but that square root is s, so I could divide it all by s. Now there actually would probably be a faster way to get to that answer if we were to leave it as it was. We had s squared equals x squared plus y squared plus z squared. So if we had taken the derivative of both sides with respect to t, we'd get 2s ds dt equals 2x dx dt plus 2y dy dt plus 2z dz dt. Okay, and then we could divide both sides by 2s, and we'd get ds dt alone, and then we'd have, let's see, if I factor out the 2, we have x dx dt plus, factor out a 2, we have y dy dt and z dz dt all over 2s. 2's cancel. We get the same result that we had before. Now the question they ask is, what if x is fixed? Then how is ds dt related to the other two rates of change? Of course, if x is fixed, then dx dt is 0. So we have that ds dt is equal to y dy dt plus z dz dt all over s. This problem, we have a circular plate of metal, and we're heating it up, so it's getting bigger. Its radius is increasing at a particular rate, so we want to know the relationship between the rate of change of the radius and the rate of change of the area. So okay, so we have a plate. As we heat it up, it gets bigger, so the radius increases. At the same time, the area is also going to increase. And the relationship between the radius and the area in a circle is that the area is pi r squared. So that's the trickiest part, is to get a relationship that always holds, right? Once we've got that, we can differentiate it. So I'm differentiating both sides with respect to t. Pi is a constant. This is a function of t, so the 2 comes down. We're going to get 2 pi r dr dt. So there's the relationship between the rate of change of the area of the plate and the rate of change of the radius. Now they actually tell me in the problem that dr dt is 0.01 centimeters per minute, and they want to find the rate at which the area is increasing, so they want me to find dA dt. So dA dt is going to be 2 times pi. Now the rate will depend on the radius, but at this particular instant the radius is 50 centimeters. So we're going to plug in 50 centimeters, and we'll plug in dr dt, which is 0.01 centimeters per minute. So if we multiply this out, 2 times 50 is 100. So we have 100 times pi. Now 0.01 is 1/100th. So we've got those numbers and those numbers, and then we have centimeters times centimeters would be centimeters squared per minute. Now the hundreds cancel. So dA dt, look at that, turns out to be pi centimeters squared per minute. A lot of the problems that we have involve using the Pythagorean theorem in some way or another. Here we've got 2 commercial airplanes. They're flying along, I guess both are at 40,000 feet, along straight line courses that intersect at a right angle. So their courses intersect at some right angle. Bet you there's going to be a triangle in here somewhere. Plane A is approaching the intersection at a speed of 442 knots. So here's plane A, and if we actually, let's just call the distance from the point where they're going to, where their paths are going to cross, we're going to call that dA dt. And then plane B is out here, and it's approaching at some rate dB dt. Okay. And at what rate is the distance between the planes changing when A is 5 miles from the intersection and B is 12 miles? So we want to look at the distance. Let's maybe call that S, for straight line distance between the 2 planes. So one plane is flying this way, the other plane is flying that way. We're actually told that dA dt, the rate at which this distance is decreasing, is negative 442 knots. So 442, we'll call them nautical miles per hour. That's a knot. Okay, and dB dt is its distance to the intersection point is also decreasing at a rate of 481 knots. Okay, and they give us this relationship. I think these must be in, since they're doing it in knots, let's assume that these are nautical miles as well. If not, I guess they give us enough information to convert here, since we know for a regular mile it's 1,760 yards, so we could convert between the two, but let's assume everything's in nautical miles. Okay, what we need to do is figure out ds dt, right? That's what they want to know. Obviously it will be negative, but what will it be? Well, let's write out a relationship here, and we can see that that's this right triangle, s squared, is going to have to be a squared plus b squared. Now notice this is a relationship that always holds true. It's kind of tempting when you see the 512 to just say, oh, well, s is 13, but you couldn't differentiate that because that doesn't hold when you change a or change b. So you have to have a relationship that's always true. Now what we're going to do is differentiate both sides with respect to t, so we get 2s ds dt and 2a dA dt and 2b dB dt. Okay, so now we can figure out what ds dt is because we know these numbers. We know at this particular instant what a and b are, and if you know a and b at a particular instant, then you can find s, right? In this case, a is 5, so this is 25, and b is 12, so this is 144. 25 plus 144 is 169, and the square root of 169 is 13. So we know that A is 5, B is 12, and therefore S, the distance between the two planes, is 13 nautical miles. So put that all together, and we have ds dt is going to be equal to 2 times a, that's 10, times dA dt, which we decided was negative 442, plus, let's see, 2 times 12 would be 24, times negative 481, all divided by 2s, so that would be divided by 26. So we get ds dt is, let's see, negative 4,420. Let's see, in this number, I'm going to pull up my calculator, that's 11,544. And we got to divide that by 26. And when we do that, we get 614. So copy it over here, just plugging in the numbers. ds dt is equal to negative 614. All these numbers were in nautical miles per hour, so knots.